Greetings, I am Dina Ingram. I'm a marketing manager here at Eurofins EAG Laboratories, and I would like to welcome you to the next installment of our EAG Experts series, focused today on elemental analysis with ICP. Prior to hearing from our three experts today, I would like to go over a few housekeeping items with you. All attendees have been muted. However, if you have additional questions that arise during the presentation, please ask them in the questions panel located in the bottom right corner of your screen. If time permits, our team will answer these questions during the Q&A at the end of the event. Thank you to all of those that have pre-submitted questions. We have received over 200 questions and unfortunately are not able to answer all of them during the live webinar today. These questions are important to us and our team will be following up with you with the answers to your questions in the coming weeks. Lastly, post-webinar, you should receive a short survey and your feedback is greatly appreciated. Now, I would turn it over to Frona P. Wilson, who is the RGA Director here at EAG, who will be the moderator for today's event. Frona?
Thank you, Dina, for the introduction. It looks like we have a big virtual crowd out there today. Thank you, everyone, for joining us. Our experts for today are from our lab in Syracuse, New York. This particular site offers several different testing techniques, including GDMS, ICP, IgA, and a whole suite of gas analysis and thermal techniques. But today we are focusing on ICP applications. We have a lot to cover, so I will get started introducing our three expert panelists that will be presenting today. Christina Pompo joined EAG Labs in 2017. She's a team leader for the ICP group and brings with her a Bachelor of Science degree in chemistry from Lemoyne College, along with 7 years of experience specializing in ICP-OES analysis and advanced digestion techniques. Along with Christina, you will hear from Kevin Lusick. Kevin's 18 years of experience contributes to his expertise in ICP-MS analysis and advanced digestion techniques. He has been a valued member of the EAG team since 2014. And finally, you will hear from Dr. Andrew N. Zipkin. Andrew's one of our senior scientists joining the team in 2021. He has a bachelor's degree of science in biology and society from Cornell University, as well as a PhD in philosophy in hominin paleobiology from George Washington University. His focus at EAG Laboratories is on LA-ICP-MS and ICP-MS. So what can you expect from today's seminar? We'll start with an introduction to Eurofins EAG Laboratory. After that, I'll explain something you may have seen in our literature called the SMART chart. Then our presentations and Q&A will be broken up into four sections, starting with ICP overview, ICP-OES, ICP-MS, and LA-ICP-MS. After that, we will answer any additional questions from the audience that we have time for. So let's get started with a little bit about Eurofins. Eurofins is a global leader in testing with more than 58,000 employees, 900 laboratories in 54 countries. EAG is a division of Eurofins specializing in materials testing with over 40 years experience. We have more than 600 employees with 20 laboratory facilities all over the world. These laboratories include more than 25 different types of testing equipment and support over 5,000 clients. As you can see from this map, we recently opened a new battery lab in Sunnyvale, California that will work in partnership with the new battery testing lab we have here in Syracuse, New York. If I had to describe EAG Labs with 2 words, it would be problem solvers. As highlighted in this flowchart, EAG helps to solve commercial challenges from concept all the way through the product lifecycle. Client success requires control and optimization at all stages. We help with R&D, prototype development, pilot studies, manufacturing, reliability, and failure analysis. EAG provides the knowledge and appropriate tools to help clients faster and better. This next slide shows all the different industries that we can assist. Our highly skilled employees use industry-leading, state-of-the-art technology and take advantage of scientific and engineering know-how to accelerate innovation through creative problem solving, objective analysis, and expert interpretation of data. Now let's look at this SMART chart. SMART is an acronym for spectroscopy, microscopy, analytical resolution tool, and it shows the techniques we have at EAG. This SMART chart allows us to compare the spot size and detection limit of each technique. The techniques are color-coded according to the description at the lower left. For example, the dark blue areas provide elemental information primarily, while the green shows imaging information. The x-axis shows the range of spot size from 1 centimeter at the right down to 1A at the far left. The y-axis shows concentrations either in atoms per cubic centimeter at the left or in atom concentrations at the right that range from 100% at the top down to 10 parts per trillion at the bottom. So within the box, you can select your technique based on the detection limit you need and the size of the area of your interest. Outside the box are techniques that don't quite belong in the chart. The techniques on the right, for example, don't necessarily have a spot size associated with them. They are basically bulk composition techniques that can consume your entire sample, and they have the detection range shown at the top to the bottom. The techniques at the bottom are basically imaging techniques and don't provide composition per se, but they do have relevance with respect to the spot size on the x-axis. You can download a copy of this using the QR code that you see there. And now I will turn it over to Christina and Kevin to start off the presentation showcasing our ICP applications.
Awesome, thank you, Verona. So I'm Christina, I'm here with Kevin, and we're going to start by giving a kind of brief overview of ICP-OES and MS. So these techniques are similar in that they have the same sample introduction system, so they both require that samples be in a liquid form prior to analysis. So any solid samples would need to be digested or dissolved in acid prior to being run on the instrument. Both techniques also have a argon plasma torch where the sample is ionized, and where they differ is in their detector. So optical emission spectrometry, or OES, analytes are separated by wavelength, and for mass spec, or MS, analytes are separated by their mass to charge ratio. Here at EAG, we predominantly use ICP-OES for major or minor concentrations, and for MS, we use that for the traces. So here's a typical setup of an ICP-OES. So we have our digested sample solution here. The sample gets pulled through a probe by a peristaltic pump where it gets put into a nebulizer and mixed with argon to create a fine mist. From there, this gets injected into the plasma, where the sample gets dried, vaporized, atomized, and ionized. From there, the atoms or ions will lose an electron to reach an excited state. And when they come back down to that ground state, they'll release energy in the form of light. And that light is element specific. So the spectrometer will separate the wavelengths, and the detector will identify the wavelengths and their relative intensity. And that intensity directly corresponds to the concentration of that analyte in the sample. So this is an example of the spectra we see from an analysis. So this is in aluminum wavelength, and on the right-hand side here is the typical sequence that we would set up our run in. So we have our blank, our low, middle, and high standard, and then a QC second source that we usually make at the same concentration as our S2, and then our sample replicates, so these blue and pinkish lines. So we build our calibration curves so that the samples are actually bracketed within our low and high standard. And because we have those standards at known concentrations, from there we're able to calculate how much of that element is actually present in the sample. So that was an example of a standard ICP-OES analysis. We also offer what's called high performance ICP-OES. And it's a little different in that we don't build a calibration curve, but rather we use exact matching and sample standard bracketing to calculate concentrations in a sample. So this is actually adapted from a NIST procedure that they developed to quantify their reference standards. So how we do it is we build standards at the exact same analyte mass fraction as the samples and analyze them in a sequence of standard replicate 1, sample replicate 1, standard replicate 2, sample replicate 2, and so on. That entire sequence gets repeated 5 times, and so we're able to correct for drift. And the intensity of each analyte is directly ratioed to the intensity of that analyte present in the standard to calculate the concentration. The results are also provided with a total global uncertainty where all areas of error are taken into account. And this purple table is an example of what our how we process high performance data. So we have all sources of error, and they all get calculated and totaled together to provide the total expanded uncertainty. And because of this, this method is able to provide about 1% accuracy as compared to standard ICP-OES, which can give 3 to 5% error relative. And now I'll give it to Kevin, who will talk about the ICP-MS setup.
Hello. So again, it's the same sample introduction system, same pump. Where we start to differ is in this ion extraction interface. So as the ions come out from the torch, they're at atmosphere. So what's missing in the schematic right here is a vacuum. So the vacuum acts to pull the ions from the injector through a series of cones that get narrower and narrower to focus that ion beam of the elements of interest. And from there, it's going on to an ion deflector. So any uncharged particles or neutrals that would contribute to background noise from the instrument are filtered out. And we're left with positive charged ions flowing towards our quadrupole. Before we hit the quadrupole, though, we can actually add in a gas exchange, collision or a reaction gas, usually helium or ammonia is used in this cell right here. The analytes go down into our quadrupole, where they're on an opposite charge of positive to negative. So as the lighter elements pass through, they're pulled off into the detector, and the heavier ones travel on down. So as the ions go into that mass separation, being separated by their mass to charge ratio, it hits a dynode. And as that dynode and the electron hits the dynode, hits another dynode and another dynode, and those electrons cascade down, and they go from a stage of pulse, counts per second, up into analog, where you start seeing over 1 million counts per second. So our method is based off an EPA method, trace metals in water. So we build a standard calibration curve, and we look at the correlation coefficients. We also use quality control checks throughout the run, matrix spikes, blank spikes. This is a typical type of report that's generated by the instrument, where it will give you your raw intensities, your internal standard recoveries. So from your raw intensities, where you're telling the calibration curve what the values are, that's how it's generating the unknown sample results. So everything's related back to this quantified quantifiable curve that you see right here.
So because obviously samples need to be fully in solution for analysis, we got a lot of questions on sample prep, what a typical prep looks like, what methods we use, what acids we use. And because we deal with such a wide variety of materials here on a daily basis, we use all sorts of methods for digestion.
So the most important part of ICP or ICP-MS is the prep. If you have a bad prep, no matter how good you are analytically, it's not going to account for that. So prep it's only a small part of the work, and the data processing is the larger part, but the most important step is always going to be the sample preparation here. We use pretty much every acid you can think of besides perchloric here in-house. We use nitric, HCl, a combination of the two, aqua regia, reverse aqua regia, peroxide, HF, anything we can think of. So what we generally do is for MS, we're always trying to get the smallest amount of acid to digest our sample to avoid some things we call polyatomic interferences. So we always start out like at hot block digestion with an unknown material. If that doesn't work, we process it on to a hot plate. If that doesn't work, we actually have a microwave digestion units. We actually have 3 different microwave digestion units here at EAG. They vary in temperature and pressure. They go from 20 bar to 60 bar in pressure. There's different ceramic holders in each one of them. If that is unsuccessful, we bring out our big guns. We use a power bomb system. It's a steel enclosed Teflon slug where we can hold pressure up to 80 bar for up to 24 hours. We also had questions we also do leaching and acid extractions where we just put a very small amount of acid onto a sample, digest that surface layer off, and analyze that. We also employ ashing for carbon and polymer materials to kind of burn that matrix off to get rid of any matrix effects.
And we also got some questions on what materials are difficult to digest, if there's some things that can't be digested. With the methods that we have here, these are some examples of things that it can be challenging to digest, things like sintered ceramics, rocks, and certain types of glasses. Rocks, I know a common digestion method for them is fusion. That's not something we do here just because a lot of the flux needed to fuse samples gives a lot of carryover issues when we're running, full scans on a daily basis. It's doesn't work the best if you're seeing high amounts of background due to a flux. So it's not something we do here. We do, because we do have issues with these could potentially be good candidates for laser ablation, which doesn't require that sample preparation step that Andrew will talk about later.
We also fielded a lot of questions about graphite, carbon-containing materials. How is this method best applied to carbon-containing bulk solids? How to measure non-solubles, example carbon. What analysis technique is the most suitable for high-purity graphite, or the best way to analyze graphite? So we employ an ASTM method here. It's for trace metal content and analysis in carbon black. We know that some elements volatilize under ashing. So we employ a 2-step digestion and analysis. So for transitional metals, we're using a high temperature ashing to kind of get rid of that carbon matrix. After we ash the material, we add a very small dilute amount of acid, bring it up to volume, and then we'll analyze it. The other part, to get those volatile elements in, we use microwave acid extraction, and from there we take the sample, microwave it under pressure, and then we'll take the analyte, or we'll take the sample out, and then we'll filter it, and then dilute it and get it ready for analysis.
And we also got some questions about limitations for the techniques. So for OES, aside from obviously the fact that a sample needs to be digested, there are other factors that are limitations. One would be matrix effects. So we run a lot of heavy matrices through the instrument with a high amount of total dissolved solids. And with that, you'll see matrix effects or background shifts because of the difference between your standards and your samples. Another thing would be instrument drift. You can see that daily, even just on a single run or long-term through weeks or months. Another limitation, OES is not ideal for trace analyses. Like I said, we're running really heavy matrices for like alloys for composition because we kind of bombard the detector with high total dissolved solids, kind of lose the sensitivity on the low end and makes it hard to recover those trace elements. Another thing would be spectral interferences. For running an alloy with like 10 to 12 components in it, the more elements that are present in the sample, the more likely you're going to see spectral interferences on those wavelengths. So some solutions to these issues, internal standardization. So we spike our standards and our samples with a known controlled amount of an element that's not present in them to kind of standardize the run and reduce those matrix effects. We also have specialized sample introduction systems. So the nebulizers that we use are specifically built for high total dissolved solids. Again, that helps limit the matrix effects that we see. To kind of monitor that instrument drift we see, we do long-term statistical process control, or SPC. And OES also has two viewing modes, axial and radio. Axial mode is a lot more sensitive, but because it's sensitive, you see a lot more interferences. It's not that great at mitigating those matrix effects. So it's easier to see the low end, but you'll see a lot more interferences that way. On the opposite side, we have radial mode, which is less sensitive, but it's better at lessening those matrix effects. So you see less interferences. So it's kind of a balance there. A way to kind of combat those spectral interferences would be to analyze multiple wavelengths. So we don't just select one wavelength for every analyte that we're running. If available, we'll select multiple for each, and that way we're able to validate the analysis. And also, if we see interference on one line, we have another one as an option.
So we had questions on limitations for MS and the solutions. So limitations for MS would be interferences such as isobaric interferences. So that's an interference where you're sharing the same mass to charge ratio. So if I was running, say, an iron sample, there's an iron isotope at 58, I wouldn't turn on nickel 58, I would turn on a different isotope of nickel. And then you've had polyatomic interferences where in the plasma, things will combine together. A common example of that would be argon plus oxygen, which leads to 56, which is the mass of iron. Another common polyatomic is if you're using any chlorine in the digestion, argon plus chlorine is arsenic 75. So again, we have the same issue, instrument drift, daily and long term. Where OES is not ideal for trace analysis, we're not ideal for great weight percent. So if you have a nickel alloy, for me to dilute down to ppb range to get a nickel number, you're looking at a serial dilution where you're up to a 1 million X dilution. Majors are best handled by OES here. And we have higher reporting limits versus a direct sampling technique. So our samples, when we get them, it's either a metal or a steel. So you're starting off with digesting the sample. So it's essentially a dilution on the sample itself. Additional dilutions are also required to reduce the total dissolved solid plasma loading that we see. So heavy matrices tend to overwhelm the detector, and you have to dilute the sample down even further. So solutions to these, we use multiple isotopes and multiple gas modes. We also use internal standardization. So we employ up to 10 different internal standards because we are dealing with a lot of unknown materials here on the MS side. So we're trying to keep the internal standard within 40 atomic mass units. So we can plug and play, like, oh, this sample has indium in it. Oh, we'll have to switch to, say, terbium or cesium as our internal standard. Again, we also employ the long-term statistical process control, We're measuring 3 different mass ranges. We're measuring a low, a mid, and a high weekly and monitoring for trends. We also employ that specialized introduction system as well. PFA nebulizers, quartz injectors, and then some ways to combat, again, those polyatomic interferences. We have the universal cell, which is equipped with multiple reaction gases, primarily helium and ammonia.
So a couple other questions we got. What is the sensitivity difference between ICP-OES and MS? So we touched on that a little bit, but here we predominantly use ICP-OES for major and minor elemental compositions. So anything from 0.05 weight percent or 500 ppm and above, depending on the sample matrix. And for MS, it's ideal for trace concentrations, anything 1 weight percent and below, down to sub ppm, again, depending on the material. And that's why OES and MS work well together. Depending on your needs, we're able to give you a full picture of, majors and traces with the 2 techniques.
Another question we fielded, what are the limits of detection? So reporting limits here for MS are based upon the lowest calibration standard that we have, and that's where you're starting to see that 3 to 5 time differential from our calibration blank and the signal to noise ratio on the instrument. From there, any weight that's used, so if we use a smaller weight or a different final volume, those all come into play for the reporting limit. So limits are also matrix dependent, so you're not going to get the same reporting limit for, say, 18.2 DI water as you would for a pure tungsten metal. So the water could be taken directly out of your DI system, not run at a dilution, run it as is, where the tungsten, you're taking it, digesting it, further diluting it, which is affecting that reporting limit. Are there any elements which cannot be detected with this method? Gases, helium and hydrogen, are below the mass detector range. Argon and nitrogen, they're just everywhere. There's no real good resolution here for that. Halogens such as fluorine, noble gases. We have carbon down here. We can measure trace elements in carbon, but we cannot measure carbon in samples.
And lastly, how do you know you can trust your results? So we have a lot of different acceptance criteria and steps that we take to make sure that our analyses are validated. So some things for ICP-OES, we analyze multiple wavelengths per element. If we're seeing a lot of wavelengths that don't agree, or there's only one wavelength available for a specific element, we can do a spike study. So spiking a known concentration of that element into our sample and checking the recovery to verify which wavelength is giving the correct concentration. Similarly, for ICP-MS, we analyze multiple isotopes per element when available, and as Kevin was saying, that can help mitigate any potential polyatomic interferences. For each technique, we run a second source QC check before and after our samples. So that is a separate standard that's built with different stocks than what we build our calibration curve with. So it validates our curve as well as monitors instrument drift throughout the run, depending on how many samples you have. If you have, tens of samples and your run's going to be hours long, you can also put in QCs throughout the run to verify. For both techniques, we also build our calibration curves with NIST traceable stock solutions. So our results are fully quantitative. And for each wavelength or isotope, we verify linearity for everything with different acceptance criteria for each. So for ICP-MS, our correlation coefficient needs to be above 0.997, for OES above 3.9s. OES also calibrates using matrix matched calibration curves tailored to the composition of the sample. So we don't just have one calibration curve that we're running every single matrix with. We build specific calibration curves for each material. So if we're running an aluminum alloy, we're building that curve to, kind of mirror what is actually present in an aluminum alloy. and this also helps reducing those matrix effects. For ICP-MS, we also analyze a blank and a matrix spike during each analysis, so a BS and an MS. So again, spiking known amounts of your analytes directly into your sample, and a blank spike. The blank spike just confirms that the instrument in the run is operating properly, and then your matrix spike confirms that you're actually recovering those elements in the sample itself. So now I will turn it over to Andrew, who will discuss laser ablation ICP-MS.
All right, hi there everyone. I'm Andrew Zipkin. I work with Kevin and Christina at the Syracuse, New York lab of EAG Laboratories. I'm the site subject matter expert for anything laser microanalysis related. So if we're talking about, say, laser ablation or laser-induced breakdown spectroscopy, techniques like that generally. So let's see if I can get these slides advancing. All right, so just to start off, laser ablation is still ICP-MS. It's just a solid state sampling variation that was originally invented for geochemistry. So if you need to analyze discrete regions in a mineral grain, for example, you can't just digest the whole rock the mineral's in. You're never going to see the information that you actually need that's spatially specific. So by using solid sampling, we know what we're analyzing at any given time. So there's some pretty important distinguishing characteristics of laser ablation compared to solution MS. So first, material is introduced to the mass spec in a solid state as nanoparticles that are removed from the sample surface by the laser. Second, it's a microanalytical technique as well as being spatially resolved. So you can see in this image off to the right, this is from the USGS microbeam lab in Denver. Those are ablation craters on the order of about 100 to 150 micrometers. So that's the result of firing laser pulses at a fixed location on a sample. And we can get down to as small as 10 micron diameter spot sizes. Actually, the laser behind me can go down as low as 1 micron, but typically we know we get better results in the 10 micron plus range. We can go smaller, but 10 to 150 is out the usual range. And finally, spatially resolved. So that means we can associate chemical data with locations on a sample. That means we can do things like measuring gradients of elemental abundance. We can target inclusions that shouldn't be in a sample, but somehow got there. We can compare defect to non-defect areas, and we can actually make false color heat maps that visualize elemental abundance. All right, so what does this actually look like in terms of hardware? So again, it's still MS, so what we've changed is the front end. We don't have an autosampler with a probe and a peristaltic pump. What we have is a laser and a cell or chamber that holds the sample. So starting from the top right, this schematic is indicative of sort of our workhorse laser, the Applied Spectra J200, which is actually a tandem laser ablation and lib system, which is pretty neat. So the laser source here is solid state. It's a neodymium doped yttrium aluminum garnet laser source. It's a synthetic crystal that emits at 1064 nanometers. Now, we don't actually use the light at that wavelength. The laser builds resonance to get that down to 266 nanometers, which is the actual wavelength we want to use on our sample. That gets focused through an aperture, bounced off a mirror, and then directed into the sample cell, which is just a hermetically sealed box pressurized with either argon or helium that acts as a carrier gas. So the laser is going to go and ablate the sample, and the carrier gas will sweep those ablated particles into the ICP-MS plasma torch, where they're ionized just as in solution ICP-MS. And from there, it's all the same thing. Now, in addition to the J200 laser, what you can see behind me, that is the ESL Image Geo 193 LA system. So this is actually not a solid state laser. It's an argon fluoride excimer gas source laser. So this is actually a 193 nanometer wavelength, which is, in my opinion, strongly preferable to 266 nanometers. It tends to cause far fewer undesirable effects on your sample, like cracking and melting, sort of off-target alteration. 193 is the most commonly used one also in geoscience. It's really good on refractories like quartz, things like that. So we have this laser back here that was installed in the fall of last year. It's actually an imaging optimized laser. So even though we can use it for routine sort of spot and line analysis, measuring concentrations, it's also a very, very fast washout laser. So it moves the particles out of the sample chamber and into the mass spec very efficiently. That way we can fire the laser quickly and raster it over the sample quickly and map an area in a reasonable amount of time. And that also means it's future compatible with time of flight mass spec. This is really the future of laser ablation, is not using it with quadrupole mass spec, but time of flight is essentially near simultaneous measurement of all your analytes. That means you can do mapping much more efficiently, but also you can do full scans by laser ablation with a much better quality of your data than if you're doing sequential mass spec, where you're pairing sort of a transient signal technique with sequential MS, which is not the best combination. So how does this actually work? What happens when the laser's firing and matter and laser energy come together? So from the top to bottom on the right, that diagram over there, that's just showing over about a millisecond what happens when a single laser pulse interacts with the sample material. So what you're going to do is the laser energy is going to induce heating, evaporation, and ionization of the sample. So you're actually ionizing it in situ right there, which is incidentally also how you do laser-induced breakdown spectroscopy using the same sort of laser. So you're going to form this sort of hot ion soup of excited particles. They're going to de-excite back into atoms, flocculate together into nanoparticles, and then those are carried into the MS by that helium carrier gas stream. And again, it's going to be ionized by the argon plasma, and so on and so forth. At this point, it's just the same as solution ICP-MS. Finally, an important difference here from solution MS is that laser ablation is producing a transient signal. So this is time-resolved data, much like you would get in, say, gas chromatography mass spectrometry. So you can treat this time-resolved data two different ways. You can either deliberately exploit its time-resolved properties and see what happens as a result of every pulse of the laser. So this figure off to the right from about almost 40 years ago now, in the original publication announcing laser ablation, that's just showing the signal response on the y-axis compared to time on the x-axis. So those peaks are just the result of each laser pulse being fired. So that's what's called the single pulse response. How much signal do you get from a single laser pulse, and how long does that signal last? So if you want to use time-resolved data and exploit its properties for mapping, you can do that, or you can fire the laser quite quickly and raster it over the surface of a presumed homogeneous sample to create a pseudo-steady state signal. So that's trying to essentially replicate something similar to the signal you would get from solution ICP-MS, where you're trying to do sort of a pseudo-bulk analysis. So this is going to be a pretty information-dense slide, but I think it's really going to answer a lot of the questions that I got asked in advance of this webinar. So let's dive into this. So strengths. Great thing about laser ablation is that we can do trace, major, and minor elements all in the same analysis using the same instrument. We don't need to do OES and MS for doing laser ablation. And the reason for that is that we're not diluting the sample at all. It's being analyzed as a solid, but also we're analyzing a tiny amount of material on the order of picograms typically. So we can really exploit the full linear dynamic range of an ICP-MS detector and do trace through major all in the same analysis. So I mentioned it before, it's microanalytical, which is great. It means we can target things that would be lost in larger spot size analyses. If you've got microscopic defects or inclusions, things that you really need to see what that is, not that plus the surrounding area. So we can do uncalibrated signal, semi-quantitative concentration, or fully quantitative data as needed. It really depends upon what question you're asking. I work with all of our clients to figure out what they actually need. In many cases, what you really need is just to say, is this element present or absent? It shouldn't be here. Is it here? And that you can do that uncalibrated, and that's just fine. So another great thing, it's a very flexible technique. Sample type isn't constrained by its conductivity, its vacuum stability, whether it's organic or inorganic, its transparency, or whether you can digest it. So as Christina and Kevin mentioned earlier, laser ablation is a viable option for some really nasty refractory materials that are a nightmare to get into solution or just completely impossible to digest. From my perspective, some other advantages are it's relatively fast because there's no wet chemistry prep involved, no digestion. It's clean. There are fewer opportunities for contamination because you're not adding any acid reagents, you're not diluting it with water, you're not putting it in all these various vessels. There are just fewer chances to dirty your sample of something from the environment. And finally, it's relatively green. We're not generating any caustic hazardous waste, and the only things we're consuming are helium, argon, and electricity. However, always two sides to a coin. So limitations, same problems as solution ICP-MS. Can't do noble gases, halogens, oxygen and nitrogen are just everywhere in the environment because this is an atmospheric technique, so you have a massive background signal from those elements. You can do radioactive elements, but we don't. We are not a nuclear lab, so that's not a thing that we're going to do. We're not going to be measuring, say, strontium-90, things like that. Things we can do, but that are difficult. Carbon, you can measure at matrix levels. So we've got this massive background signal from carbon dioxide in the atmosphere. If you're measuring graphite, sure, I can see a carbon signal above background, no problem. One thing you might want to do is, say, compare two carbon-based polymers that have an inorganic loading agent in them. So one of these complex materials with multiple components, and maybe the client wants to know which of these materials has a greater ratio of carbon-based polymer to the inorganic loading agent. So I could say that this one is going to have twice as much polymer as this other material that has a larger inorganic component, something like that. Sulfur you can do, but typically we have a pretty high reporting limit, usually in the thousands of ppm. That's because we typically want to measure sulfur at mass 32 or 34, and both of those are interfered by an oxygen dimer. So 16O2 is mass 32, and 16O, is mass 34. So we have interferences from the atmosphere just parked on those two isotopes we want to measure for sulfur. And silicon, this is actually a hardware problem. You have that argon plasma torch ionizing your samples, but you need to contain that somehow. So there is a cylinder made of quartz that surrounds it that is actually the torch, as in the part of the instrument. And that quartz SiO2 torch is just shedding silicon all the time, giving you a high silicon background. So in terms of calibration, if you want fully quantitative data, you need matrix matched reference materials, and they need to be homogeneous at the scale of analysis. So there are many, many commercially available and government lab produced reference materials out there. Most of them are bulk powders meant for digestion techniques. They are not designed to be homogeneous at the scale of tens of microns. So finding calibration materials can be a challenge. Unlike solution MS or OES, you typically can't add in an internal standard element because you get a sample that's already a solid. So the way we typically deal with this is we'll measure one of the matrix elements in that material using a secondary technique like microprobe, XRF, maybe LIBS, SEM, EDS, and then we'll measure that matrix element and we'll use that value as our internal standard value during laser ablation data reduction. Or we can just assume stoichiometry. So if you've got, say, alumina, Al2O3, we can just assume the weight percent of aluminum based upon the formula Al2O3. So there is no chemical prep involved, but large or regular samples might need mechanical prep to fit in the laser ablation cell. You want your sample to be flat and smooth. You're going to get much better quality data from something like that as opposed to a really rough variable surface photography sample. And we do need samples that are stable at room temperature and free of liquids for most applications. We aren't a life sciences or bioscience lab. They do make cryogenically chilled laser ablation cells for doing soft tissue analysis, but that is not our neck of the woods. There are mostly university labs that deal with tissue samples. So first slide of questions here. I'm going to answer about 5 or 6 questions. I'm going to try and combine these together so that they're sort of related questions that can sort of, the answers will feed off of each other and sort of make sense cohesively. So first, how is calibration done with laser ablation ICP-MS? So I've been talking a lot about matrix match standards, but what does your actual analytical run look like? So much like high performance ICP-OES that Christina mentioned, we do sample standard bracketing. And this is actually derived from an ASTM method. That's ASTM E2927, which is the method for the forensic analysis of trace elements in glass. And that ASTM method actually is a pretty good reflection of how everyone builds laser ablation runs, not just for glass. It's pretty much the way everyone anywhere in the world does this sort of work. So we're looking at here, we'll start with multiple analyses of our calibrants. So let's say we have 2 matrix match reference materials, A and B. We'll do this 5 times each just to anchor sort of our calibration. And then we'll move on to our unknowns. So it'll be, say, sample 1, first replicate, sample 2, first replicate, and then we'll mix in a reference material. And this is not a calibrant. This is a completely different, also hopefully matrix match reference material is going to be used for quality control. So we're just going to look at this and see how close are the results to the reference values that are in the certificate of analysis from the manufacturer. And then we're going to add in more calibrant analyses in between these unknowns and then the next batch of them. And what we're going to do here at the end of the run, if data is collected, is we're going to describe drift in the instrument over the course of the run mathematically. And you can do this using a linear model, but actually typically with modern laser ablation data reduction software, you're going to do it using a curve or a spline. A TPS, a thin plate spline, is a mathematical descriptor of curvature. So you can essentially adjust your results for drift in the instrument over time. That can be drift up and down. It can be caused by background changes based upon your sample, have memory effects. It can be caused by the environment in the room changing. But an important thing to keep in mind is that drift in laser ablation is normal. It's going to happen, and we have mechanisms for dealing with it, which is why sample standard bracketing is the default in any laser ablation run. So how do you know if your parameters are correct? This is a two-part question. I'm assuming the person asking was asking about the laser parameters. And then how do you know if the data are correct? Are you getting results that are reliable? Good questions. So in terms of your parameters being correct, method development. This is where art meets science. There's no universal guide to what laser settings to use with what material. I mean, there might be papers out there that give their settings that, oh, we use these parameters, this repetition rate, this fluence, this carrier gas flow rate on this alloy or on this glass or on this hard tissue sample. And that's great, but in my experience, you just have to have experience. You have to spend, frankly, years dealing with many different types of material and figuring out how they behave. So it's not like there's sort of a universal set of parameters. You're going to use whatever settings on the laser give you the desired result. And the desired result is ablation, no more. You're just trying to get the sample to volatilize, turn the nanoparticles, and go into the mass spec. You're not trying to just chew up your target by using too much energy or too fast a rep rate. So these images here, these are just showing 5 laser ablation scan line troughs. So this is sort of what happens after you've ablated something on a nanopowder pellet. So this is just post-ablation microscopy. And on the image at the left, the gray one, you can see this is actually what I think is a really positive outcome. The laser only ablated where the laser was fired. There's no off-target effects. There's no cracking. There's no melting. There's no evidence of back-deposited material that's sort of mounded up like a volcano has erupted. You don't want to see that. You want to use just enough energy to ablate your sample. And off to the right, this is a false color heat map of depth, again, just done from the same microscopy data. And this just shows that these troughs are about 50 to 55 microns deep. They're pretty flat bottom, not too much slope in most of them. Also, what you want to see, you don't want to see lots of changes in trough depth. You want them to be pretty uniform. So part 2 of that question, how do you know if your data are correct? Quality control reference materials, our QCs. So we intersperse these throughout the run, and it's really important to not just put these after your calibrants, mix them in. That is the honest way to do it. Mix them in among your true unknowns and analyze them in there. That way, if there are any weird effects being caused by your unknown samples, you'll detect that. If there's carryover, for example, you'll detect that when you're analyzing your QC mixed in among those unknowns. So for laser ablation, how is depth monitored? So the thing is, actually, we don't typically know exactly how deep we've gone until after the fact. So I mean, you can do repeated passes over the same ablation pattern and tell the laser to focus down by 1 micron each time, but doesn't mean it's going to be ablating 1 micron deeper with each pass. It's just going to change the focus. So what you really have to do is this post-ablation microscopy and figure out after the fact how deep you've gone. One thing you could do, I suppose, is do lots of test ablations. So multiple passes, 1 pass here, 2 passes here, 3 passes there, and then measure those, figure out how deep you ablate with each pass, and then use those data when you're building subsequent runs in the same material and say, okay, I know each pass I'll go about 10 microns deep, maybe. But anyway, if you want to figure out how deep you've actually gone, using the same microscopy data here, you'll see we've actually taken, instead of a false color heat map, we've created a virtual cross-section here. So you can see the sort of undulating line at the bottom of that image. That's just showing the cross-section of those 5 ablation troughs. This is all just derived from Kient's VHX microscopy data, which is a really great tool that we use every day. Another thing you can do that we offer is stylus profilometry. This literally has a mechanical tool that traces surface topography over your sample. That works very, very well. The problem is you don't always want to touch your sample. It might be something like this nano powder that's very fragile, that will crumble, or it might be a contamination risk. So really, we tend to prefer doing microscopy here instead of using profilometry. And on to the next, if it wants to advance. Let's see. All right, there we go. So next question, can you use this technique to depth profile a sample, and can it be used with air sensitive samples? So I'm gonna guess that the person asking this has got a very specific application in mind. So part one of this, yes, we can do depth profiles. However, I have a strong preference for doing these in cross section rather than burrowing top down with a laser. You can do a top down depth profile with laser ablation, but there are several problems. One, the laser is going to lose focus as it goes deeper and deeper. And two, you're going to induce a phenomenon called downhole fractionation. The deeper that crater gets, you're going to develop a bias against detecting refractory elements because they are going to flocculate into nanoparticles much faster than volatile elements, and they may not effectively escape that increasingly deep crater. So you're going to get a bias in favor of volatile elements and against refractory elements, and you're going to get results that are not terribly reliable if you ablate deep enough, at least in my experience. So the solution is take your sample, turn it orthogonal on its side, and turn depth into an XY dimension. And here you can see I've got this alumina sample with a embedded metal layer in the cross section, and the client wanted us to measure at 100 micron increments away just to see whether that metal is diffusing into the sample. And this is a mock-up that we have here for practice. It's also a pretty good example to use in talks like this. The other thing is, can you do this with air sensitive samples? So not routinely, but one of our lasers, the J200, actually does have a specialized sample cell that you can detach from the laser, put it in a glove box, and then load your sample to it in a nitrogen or argon purged environment, and then reattach it to the laser. We don't use this very much, but it does exist. In terms of looking to the future of these sort of samples, I heard something pretty cool recently that you have a new laser cell coming out that's got a mechanical arm with a razor blade that can open up sealed packets of battery materials that are already inside the laser cell, which is pretty neat. That way, there's no need for a glove box. Finally, has laser ablation compared to GDMS. Analysis area is much, much smaller, on the order of tens to hundreds of microns compared to 50 to 80 millimeters squared for glow discharge mass spectrometry, which is another great solid state technique that we offer here at EAG. In terms of mass spectrometry, we typically do laser ablation with quadrupole MS and glow discharge with magnetic sector. It doesn't have to be the case, but that's the way we have it set up here in this laboratory. For the interferences, in ICP-MS, we mitigate those using collision reaction gases, so helium, kinetic energy discrimination mode. We can also do mass shift reactions on triple quadrupole or tandem mass spectrometers. In contrast, though, glow discharge is going to rely on resolution for peak discrimination, so trying to tell apart those partially overlapping peaks rather than reacting them away. Big difference here is that laser ablation is very matrix sensitive. It's all about that laser energy matter interaction. A glass will not ablate the same way as a refractory superalloy, the same as a polymer. They're all going to behave differently and give you different ion yields. In contrast, glow discharge is very matrix insensitive because the atomization and ionization steps are separated. So it's really a very stable technique in which most materials behave pretty similarly. Another difference, data reduction, laser ablation needs those matrix match reference materials if you want fully quantitative data. In contrast, glow discharge, the way we do it, it's a standardless technique that relies upon fixed relative sensitivity factors, or RSFs, for data reduction. And that's, again, because it's so matrix insensitive, you have these RSFs developed by analyzing materials over years and years, and they're very stable, so you can just use those in your data reduction without using a calibrant. You can analyze something as a QC, but you don't need to analyze a reference material to calibrate your results. And finally, depth profiling. Both of these can do depth profiling, but I think glow discharge is better at top-down depth profiles within a pretty narrow range, so single to tens of microns compared to laser ablation. And that covers it for me. Thank you all.
Thank you, Andrew. I appreciate that. Thank you, Christine and Kevin. That's a ton of information. We have a lot of questions from our audience. So I will just start at the top. How do you avoid carryover effects during an analysis?
Oh, Kevin, you're muted.
Sorry.
Muted. Sorry about that. Carryover or memory effects, say you're running like a lithium sample. The benefit of being here at EAG, we have multiple mass specs. So one issue is the lithium is going to remain for a while, but you can always use, we have such an array of different materials we're working on, partial scans. We're not always doing full scan analysis, so we can use other samples to kind of clean that matrix effect out for us. We can change the sample introduction system, change the interface on the cones, leave for longer washouts, but primarily what we're doing is just using other samples to kind of like wash that effect out for us. So that's one of the benefits of having multiple mass specs here.
Yeah, and for OES, luckily that's not a huge issue for us. We don't see a ton of carryover. It's kind of just using your judgment in terms of scheduling. You wouldn't want to run an aluminum alloy and then immediately after that try to analyze for trace aluminum. We run pretty strong rinses with our runs and in between, so we're luckily able to wash out the matrix in between analyses, and you don't see a ton of carryover effects. But if you do, we would change tubing, change out your sample introduction system, and then you're good to go.
All right, thank you. Next question, what strategies can you use to prevent drift effects from occurring when you have a high volume of samples to run?
So typically,
just as a note, this will be our last question due to time, sorry.
Okay, drift effects. So MS, we put on runs that are 20 to 30 hours over the weekend. What we do to kind of mitigate that effect of drift is you want to keep your office temperature constant. You don't want to see giant changes from hot to cold during the analysis run. What we also do is bracket in multiple calibration checks to make sure that the instrument isn't drifting. But if you have an extended issue or you have a problem with an element drifting and it's a known, we also can bracket in a secondary calibration into the run. So that's some ways we get around drift effect here.
All right. Well, thank you. I'd like to make one more comment about Eurofins EAG laboratories. There's several reasons to choose us for your analytical needs, but I think the most important is stated right at the top, and that's client confidentiality is at the core of our business. We're a global leader in materials testing services with a broad range of instruments and expertise that leave us poised to take on even the most challenging materials and engineering related issues. Thank you all for joining us. We appreciate it. And now I will turn it back over to Dina.
Thank you to our experts and to everyone for attending today's Ask the Expert webinar. If we didn't get to your question today, we will be following up in the coming weeks with answers to your questions. If you have any more, please send them in the chat or via the email address on your screen. As a reminder, once you leave today's webinar, there will be a quick survey that will pop up, and we would greatly appreciate your feedback. As a note to our upcoming events, we have a in-person coffee and conversations event being held at our New York lab on July 30th. This event is an opportunity to speak with our experts directly and also tour our lab. Space is limited, so please register. On behalf of EAG Laboratories, our experts, and Frona, thank you for joining us today, and have a great day. Thank you.